Hey everyone, this is Derek, and in this video we're going to find zeros of polynomial functions. And so we have found zeros of quadratic functions, and we had several ways of doing that. We could factor if that worked, we could complete the square, we could use the quadratic formula. But once we get to something over degree 2, it starts getting a little bit dicier as to how to solve those. And so that is what this section will be about. I'm going to start with the remainder and factor theorems. There's a lot of theorems in this section, and I'm going to go through that part sort of quickly and just try to show you what they do. But let me talk about the remainder theorem for just a second here. So if we have a polynomial like this, f of x is divided by some other little polynomial like that, then the remainder of the value is the same as the function evaluated at that point. So what that means down here is if I do this synthetic division and I get this remainder of 10, and remember with synthetic division, we're dividing by the 0, and so that lets us change the signs and add. But so when I do the synthetic division here, my remainder is 10. If I put 2 into this polynomial, it should also come out 10. And so just to kind of remind you how the synthetic would work, we'll do our 2 here, and then I'm just copying down. Careful right there where it goes from the fourth to the second. We get that 0x cubed term, so I'm needing to put the placeholder, and then minus 5 for the x squared, and then the invisible 1 on the x minus 4. And then for synthetic, remember, we bring down the first number, and we say 2 times 2 makes that 4, and then we get to add because we changed the sign. We're better at adding. So then 0 and 4 makes 4. 2 times 4 makes 8. Negative 5 and 8 makes 3, and then 2 times 3 makes that 6, 1 and 6 makes 7, and then 2 times 7 makes 14, negative 4 and 14 makes 10. And so our remainder is 10. The way they phrase this question, it didn't ask for it, but also if, and this is what the remainder theorem is saying, if I evaluate this polynomial at x equals 2, it will come out to be 10. And so unfortunately, I'm on the road at the moment, so I'm having to sort of do this from the notes. But if you kind of envision taking 2 and plugging it in for all these x's, 2 to the fourth would be 16 times 2. So this would be 32. 2 squared would be 4 times 5, so that's 32 minus 20 would be 12. And then plus 2 would be 14 minus 4, and there's the 10 that it should come out. The reason why that is a little bit interesting is because if I do this division and that remainder comes out 0, that's going to give me information. That means that this is going to end up being a factor of the original polynomial, and that's where we're heading in this section. So let me show you one where it's a factor. So here we have x squared plus 7x plus 10, and then divided by x plus 5. If we think of this kind of old school, just written as a fraction, and I factor that numerator, remember what multiplies to be 10 and adds to be 7, 2, and 5, I can just reduce that out, and I can see that if I go this divided into this, it's going to come up x plus 2, which is what we're getting right here. And that's because this is a factor, so it goes in evenly, so I should get remainder 0. Okay, so for the factor theorem, this is our next one. According to the factor theorem, k is a 0 of f of x if and only if f of x minus k is a factor of f of x. Okay, that just sounds terrible, but if we look back at this last example, this is saying, if I put some numbers in here, according to the factor theorem, let's say negative 5 is a 0 of this function right here if and only if x plus 5 is a factor. So yeah, that makes sense. Negative 5 is going to be a 0 of this thing if this is a factor. So that's what the factor theorem states. And what we can do with it is a little bit more interesting. So given a factor in a third degree polynomial, we can factor the rest of the polynomial. So our steps are going to be, we're going to use synthetic division to divide the polynomial, and then to confirm this is 0, and then we will write the polynomial as a product of the factor and then the piece that I just got. You can kind of see what I'm doing down there. And then if possible, factor the quadratic. If not, then we're going to probably use quadratic formula or completing the square. So let me show you these steps with this example. So I'm told that x minus 4 is a factor of this. So what that's going to let me do is, if x minus 4 is a factor, 4 is going to be a 0, and I can use synthetic division instead of long division, which is terrible, to figure out what would be left over if I divided this into that. And so that's what I'm doing here. Same synthetic that I just did on the last couple, so I won't go through all the steps. But notice I get this remainder of 0 right here. And what I'm doing now is I'm saying x minus 4 times this part would make this original function. So bringing down my x minus 4, from there's my 0, x equals 4, and then here's the what's left, the quadratic. And there's nothing that multiplies to 2 and adds to be negative 4, so that leaves me either completing the square or quadratic formula. I went with completing the square down here, so I brought my 2 over, and then I did half of 4 would be 2 squared, add that to both sides, so plus 4 and plus 4. Then remember, we do our root on each side. This gets us our plus or minus root 2 over here, and then that undoes the square on this side, and we add that over. So all of our real zeros, and these are they're complex. I'm sorry, they're not complex. They are irrational, I misspoke there, but they are still real zeros. So these are actual numbers, and those are where you'd find the x-intercepts on the graph. So x equals 4, and then our first one is the 2 plus root 2, and then our second is 2 minus root 2. So if we're given one of the zeros of a cubic, we can find the other two fairly easily. So up next we have the rational zero theorem. And what the rational zero theorem does is lets us identify the possible real rational zeros. It will not tell you any of the complex zeros because those aren't real, but it will identify all of the possible real rational zeros. The definition up here is pretty formal. Basically what this is every rational zero, f of x, has the form p over q, where p is a factor of the constant term. So like in this example where p is a factor of 10 and q is a factor of the leading coefficient, which in this case is this 2. So this is just kind of giving the general form of a polynomial and then using this language to describe it. So what we want to do is we want to find all the factors of p, which again in this case is 10, all the factors of q, in this case is 2, and figure out all those possible ratios, and then that is the list of all of the possible real rational zeros for this polynomial. So for p, we have 1, 2, 5, and 10. And we always do, we're going to have this plus or minus in the problem, so that's what's going to account for that sign there. And then q is 2, so its factors are 1 and 2. So the possible real rational zeros are going to be 1 over 1, which is 1, 2 over 1, 2, 5 over 1 is 5, and 10 over 1 is 10. And then 1 over 2, there's our half. 2 over 2 reduces down to 1, and we already have it. 5 over 2, that one's new. 10 over 2 reduces down to 5, which we already have. So as plus or minus, we have 1, 2, 3, 4, 5, 6. So that'd be 12 with this double sign there, the positive or negative versions. So 12 possible real rational zeros. So it doesn't, well actually since this one's a cubic, it has to have at least one. So whatever this one's at least one, possibly 3 more rational zeros would be, are on that list. And then what we do with this is we use this for kind of figuring out what the things are that we could check, and I'm going to show you an easier way to do that because it's 2021 when I'm making this video, and we have graphing calculators. So if you don't have a graphing calculator, you can use Desmos. On the exam you'll have to do one by hand, and that's kind of a drag, but if you do have a graphing utility about, you can use that and kind of shorten this up. So let me show this next example where I'm going to actually, so this was just list the zeros, so there they are, that's our p over q, and the next one is asking me to actually use the rational zero theorem to find the real zeros. So we're still going to do this p over q thing. In this case it's nice because q is 1, so it's just going to be all the factors of 12. Unfortunately there's quite a few of those, so 1, 2, 3, 4, 6, and 12 are all things that go into 12. And so our real zeros are going to be plus or minus one of those, or all 3 of those, we'll see. So I can sit here and start doing synthetic division. I can go 1 goes into this thing, and then I will find it doesn't come out to 0, and if it doesn't come out to 0, that means it is not a factor. And then I would try -1. Does -1 go in? And I try that one. Again, we're dividing into here just like I did in that last example. And when we do that, we find we get this remainder 0. So that's cool. That means that, remember from the factor theorem, if -1 is a 0, then that means that x minus 1 or x plus 1 would be a factor. In this case, we're just asked to find zeros, so I now know that one of the zeros is -1 right there. So I could keep trying values, but that would be terrible. If I have a graphing calculator, I could just look on my graph because they're all right here. I'll get back to that in a second. But here, since this is now x squared and x minus 12, I can just say what multiplies to -12 and adds to be 1, way easier, x plus 4, x minus 3, and then just factor to get those last two. On the last example I did, this didn't factor, so I had completed the square. You could also use quadratic formula. But I would remind you that if it factors, that's by far the easiest way to get these two, other than to just graph it. So if you do have a graphing utility, which I threw this one into Desmos, you can see right here what we're finding are the zeros. I got -4 was right there, -1 was the first one that I found, and 3 was the last one there. So I could have, if I saw this graph, I could have divided this by -4, I would have got a 0. I could have done this by the 3, still got a 0, factored what's left and got the other 2. So once you have one of them, the other 2 are pretty easy to get. Okay, and then the last thing in this section is going to be the conjugate pair theorem. And basically what this says is if you have one of the, if you have an a plus bi, something of this form, say it was 3 plus 7i, then the complex conjugate of the 0 is also 3 minus 7i. You're going to have the plus version of it and the minus version. And remember, that's because when we do the quadratic formula, we have that -b and then plus or minus the root. So if that root comes up negative, we're going to get plus or minus that answer. So that's why we're always going to have conjugate pairs. We won't have one without the other. So for this first question, a polynomial is found to have a complex 0 of -i and 3 plus 5i. Name the other two zeros that must also be solutions to the polynomial. So if I have -i, that's like 0 minus I, so that would mean I would have 0 plus I. So these are conjugate pairs. And if I have 3 plus 5i, then I would also have 3 minus 5i. And so conjugate pairs. So given these two zeros, I have to have those two. That's what the conjugate pair theorem states. Okay, so for this last one, we're going to find all complex solutions, real and non-real. We're given this polynomial. 15 is great because it can only be 1, 3, 5, and 15. Again, if you have a graphing utility, just graph that sucker and go, oh, it's going to be -3, and save yourself doing the trial and error version on this. So here I am doing the -3. And again, I get this factor of 0. Notice right here there are no other zeros, and that's because this doesn't factor. There is no number that multiplies to 5 and adds to be 4. It would if it's a -5, but it's not. It's +5. And so this has complex solutions or non-real solutions. Oops, timer. That means I'm supposed to feed my dog. Okay, and so my dog's going to go over here and slobber at me now. Okay, so this means that we have to do something other than factoring. So I again chose to complete the square, but you could also do the quadratic formula. So here I got the -3 out of there. I'm left with this. I brought this over. Did my half of 4 is 2. 2 squared made 4. Add the 4 to both sides. And then factored, so just completing the square. -5 and 4 made the -1. And remember, square root of -1 reduces to I. And then I brought the 2 over at the last step. So I started off with an x cubed, and I should have 3 solutions if all goes well. My real solution was x equals -3 from right there, and my 2 complex solutions were the -2 plus I, -2 minus I.